Today, we will delve into the classical problems of synchronization in process synchronization, a crucial concept in computer science. As we explore these problems, like the critical section problem, producer-consumer, reader-writer, and dining philosophers, we'll understand how multiple processes can safely access shared resources without conflict. These problems highlight the challenges of ensuring mutual exclusion, deadlock prevention, and fair resource allocation in concurrent systems. Let's dive into the intricacies of these issues and their solutions. The producer-consumer problem is a classic synchronization issue in operating systems, where two types of processes, producers and consumers, share a common buffer. The producer generates data and places it in the buffer, while the consumer retrieves and processes this data. The challenge is ensuring proper synchronization to avoid data inconsistencies. Key problems include buffer overflow. The producer must not add data when the buffer is full. Buffer underflow. The consumer must not attempt to consume data from an empty buffer. Semaphores or mutexes are often used to solve these issues. A producer waits if the buffer is full, and the consumer waits if it's empty. Synchronization ensures that both processes work efficiently without conflicts. The solution maintains mutual exclusion, prevents deadlock, and ensures the proper order of operations, which is vital for building stable, concurrent systems. The provided code demonstrates the producer-consumer problem, specifically for the bounded buffer problem, using semaphores for synchronization. Producer process. Produce an item. The producer first generates an item, next, that it will place in the buffer. Wait. Empty. The producer waits until there is space in the buffer. The empty semaphore ensures the producer doesn't add items when the buffer is full. Wait. Mutex. The mutex semaphore ensures mutual exclusion, meaning only one producer or consumer can access the shared buffer at a time. Add to buffer. After acquiring the mutex lock, the producer places the generated item, next, into the buffer. Signal. Mutex. The producer releases text lock, allowing the consumer to access the buffer. Signal. Full. The producer signals the full semaphore, indicating that the buffer has new data available for the consumer. Repeat. This process is repeated indefinitely, as long as the system is running. Consumer process. Wait. Full. The consumer waits until there is at least one in the buffer. The full semaphore ensures the consumer doesn't attempt to consume when the buffer is empty. Wait. Mutex. The consumer waits for the mutex to ensure mutual exclusion, preventing simultaneous access to the buffer. Remove item. Once the mutex is acquired, the consumer removes an item, next, from the buffer for consumption. Mutex. The consumer releases the mutex lock, allowing the producer to access the buffer. Signal. Empty. The consumer signals the empty semaphore, indicating that space is now available in the buffer for the producer to add new items. Consume item. The consumer consumes the item, next. Repeat. This process is also repeated infinitely. Key concepts. Semaphores. Empty. Full. Mutex. Semaphores are used to synchronize the producer, and consumer. Empty keeps track of available space in the buffer. Full tracks the number of items in the buffer, and mutex ensures mutual exclusion when accessing the buffer. Mutual exclusion. The mutex prevents race conditions by ensuring that only one process, producer or consumer, modifies the buffer at any given time. Deadlock prevention. Proper sequencing of wait and signal operations ensures that the system does not deadlock. The producer and consumer always wait for the appropriate semaphore before proceeding. This approach efficiently manages the interaction between the producer and consumer, ensuring that items are produced and consumed in a synchronized manner without overflow or underflow in the buffer. The reader's-writer's problem is a synchronization issue in operating systems where multiple processes access shared data. It involves two types of processes, readers and writers. The challenge is ensuring that readers can access the data concurrently, but writers require exclusive access. Key issues. Multiple readers. Multiple readers can read the data simultaneously without causing issues. Writer access. A writer must have exclusive access to the data, meaning no readers or other writers can access it during the write operation. Starvation. Writers may be starved if readers constantly access the data, leading to unfairness. Solutions. First, readers-writers problem. Prioritize readers over writers, ensuring no reader waits if others are reading. Second, readers-writers problem. Prioritizes writers to avoid reader starvation. Semaphores are typically used to implement synchronization, ensuring mutual exclusion and preventing data inconsistency. The dining philosopher's problem is a classic synchronization problem that illustrates the challenges of allocating shared resources. It involves 5 philosophers sitting at a round table, each thinking and occasionally needing to eat. Between each pair of philosophers, there is a fork, and each philosopher needs 2 forks to eat, one from their left and one from right. Key issues. Deadlock. Philosophers may end up in a state where all are holding one fork and waiting for the other, resulting in a deadlock where no one can eat. Starvation. A philosopher may never get both forks if others are always eating. Concurrency. Philosophers should be able to think and eat without blocking each other unnecessarily. Solutions. Mutex. Each philosopher may pick up forks using mutexes to ensure mutual exclusion. Chandy. Misra solution. This approach ensures fair allocation of resources by using a token system. Resource hierarchy. Philosophers pick up the left fork first and the right fork second, preventing circular weights. The problem highlights the importance of synchronization techniques to avoid deadlock and ensure fairness in resource allocation.
The dining philosopher's problem is a classic synchronization problem in computer science, often used to illustrate the challenges of resource sharing and deadlock prevention. In the provided code, there are 5 philosophers sitting at a circular table. Each philosopher alternates between thinking and eating. However, each philosopher needs 2 chopsticks to eat, one on the left and one on the right. Here's the breakdown of the code. Wait. Chopstick, I. The philosopher picks up the chopstick on the left. If the chopstick is already taken, the philosopher waits until it's available, i.e., wait operation. Wait. Chopstick, I1, %5. The philosopher picks up the chopstick on the right. The modulus operation ensures that chopstick indices wrap around in a circular fashion, creating the ring arrangement. Eat. Once both chopsticks are acquired, the philosopher can eat. Signal, chopstick, I. After eating, the philosopher releases the left chopstick by signaling, making it available for others. Signal, chopstick, I1, %5. Similarly, the philosopher releases the right chopstick. Think. After eating, the philosopher starts thinking, repeating the cycle. This approach can result in deadlocks or starvation, as philosophers may end up waiting indefinitely if they can't acquire both chopsticks. To avoid this, solutions like introducing a waiter or a different strategy for acquiring the chopsticks are used to ensure proper synchronization and prevent deadlock. The sleeping barber problem is a classic synchronization problem that models a barbershop with one barber and multiple customers. The barber has a limited number of seats for waiting customers. If no customers are present, the barber sleeps. If customers arrive while the barber is asleep, they wake him up. If all waiting seats are occupied, the customer leaves. The solution involves managing concurrent access to the barber shop's resources using synchronization mechanisms like semaphores. Here's a simplified approach. Customer thread. If there's an available seat, the customer waits. If no seat is free, they leave. When it's their turn, they wake the barber and get a haircut. Barber thread. If there are no customers, the barber sleeps. When a customer arrives, the barber cuts their hair, signaling the completion of the service. This requires proper synchronization to ensure mutual exclusion and avoid race conditions, ensuring customers are served fairly and the barber sleeps when idle. The cigarette smoker's problem involves 3 smokers, each with one ingredient, tobacco, paper, or matches, and a common table with a supplier who places 2 random ingredients on the table. The smokers need all 3 ingredients to smoke. If a smoker has the missing ingredient, they can smoke and place the used ingredients back for others. The solution uses semaphores to synchronize actions. The supplier places 2 ingredients and signals. A smoker checks if they have the missing ingredient. If so, they smoke, replace the ingredients, and signal the supplier. Proper synchronization prevents conflicts and ensures fair access to resources. These classical synchronization problems illustrate the fundamental challenges of managing concurrent processes. Solutions often involve semaphores, mutexes, and other synchronization primitives to avoid issues like deadlock, starvation, and race conditions, ensuring that processes can share resources safely and efficiently.